When I was in school, when I was studying physics, Star Trek used to come on. This was when there wasn't cable, network television, at 4 o'clock. So all the physics majors would gather, and we had like a little lounge, and we'd all watch Star Trek together. What's that? No, that was original Star Trek.
That's the only Star Trek worth watching.
All right, so we're going to talk about three-dimensional vectors. Now, to construct our three-dimensional vectors, we need a three-dimensional coordinate system. So what we're going to do is, whoops, I want to go the other way. We're going to take our x and our y axis that we're familiar with, and we're going to add a z-axis that is perpendicular to both. And I'm just going to make this a little shorter.
Oh, you do that? That is so cool. Whoa. Whoa.
Isometric, wow.
This is fun too.
Whoa!
Oh, what?
Whoa! Oh my god. Oh my god.
Remember watching
All right.
just like recording?
I think we're all stupid.
Alright, 3D vectors, time to learn.
And the coordinate system that we construct, we call a right-handed coordinate system. And right-handed system means if we put our arms in the direction of the x and the y-axis, our right arm extends along the x-axis, and our left arm extends along the y-axis, and the z-axis extends through our head.
Like this.
Our right arm goes in the direction of the x-axis, our left arm goes in the direction of the y-axis, and the z-axis.
My god.
If you can also think of it in terms of your right hand. Your fingers extend in the x and y along the x and y axis. Your index finger points along the x, your middle finger points along the y, and your thumb points along the z axis. Yeah. A left. Let's focus, folks. A left-handed coordinate system would look like this. It would look the same, but we would say this is the x-axis, and that's the y-axis, and that's the z-axis.
Left.
Well,
Which one are we going to be using more?
we will only use a right-handed system.
We're all right-handed.
So we are only going to use a right-handed system in this class. What we're going to do, so I'm going to say we will use this. We're going to talk about the planes, just like we in 2 dimensions we talk about the coordinate axes. We're going to talk about our coordinate planes. So we have our coordinate planes. Are the xy plane. And that is the one that we're familiar with. The xy plane is where z equals 0. That's what we've used basically our whole life. We have the xz plane. So the xz plane is, up here on the right-handed system, is this plane kind of coming out of the screen. That's where y equals 0. And we have the yz plane. So that would be this plane here. that's in the plane of the screen, if we visualize that. And that's where x equals 0. So we'll talk about our coordinate planes. And when we start talking about surfaces and graphing three-dimensional surfaces, their intersections with the coordinate planes are going to be what helps us graph those surfaces. And our three-dimensional coordinate system divides space into 8 octants. So in the xy plane we had 4 quadrants. In space we have 8 octants. And the first 4 octants go they follow along with the 4 quadrants. So the first octant is where x, y, and z are all positive. So we have 8 octants. First is where x, y, z all positive. And then they go counterclockwise around the z-axis. So the first 4 octants are directly above the four quadrants. So octant 1 is here. Octant 2 would be back behind the YZ plane. Octant 3 would be back here. Octant 4 would be up here. And then octant 5 is below octant 1. So below the XY plane here. And then they go counterclockwise around the z-axis below the XY plane. We will mostly work in octants 1 through 4, and usually in octants 1 and 2. Usually. We won't do much in the other octants. And if we think of distances from the coordinate planes, x is the distance from the YZ plane. Y is the distance from the XZ plane. And Z is the distance from the XY plane. And what we can do, we will do this in second semester. We talked about centroids and moments of planar lamina. When we get into 3 dimensions, we can talk about centroids of solids. We can talk about moments of solids, about axes, and about planes. And we'll have a much nicer way to do that when we talk about multiple integration, because we won't have to make all the simplifying assumptions that we did in the first semester. All right, so we're good so far with the idea of a 3-dimensional coordinate system. Now, just a little bit of history with in terms of vectors and working with vectors. So Aristotle used vectors to describe forces. So the idea of vectors have been around for a long time. Descartes developed the idea of resolving vectors into components that are parallel to the coordinate axes. So an x component and a y component. And vector algebra, what we're going to talk about in chapter 11, then we'll start doing vector calculus next semester, was developed by a gentleman named Gibbs, who was a mathematical physicist at Yale, and also an English physicist by the name of Heaviside. And if you remember the cover-up method for doing that you can use for partial fractions, that's called the Heaviside method. That's the technical name. He came up with that idea. And Hamilton was one of he started developing the idea of vectors, but Hamilton had a slightly different idea with vectors. He came up with this thing called quaternions that had to do with complex numbers. But they were trying to develop a language for electromagnetism, which was developing at the time. So a little historical background on vectors. All right, so our familiar ideas from 3 dimensions, or from 2 dimensions, extend to 3 dimensions. So there's really not much new information. Those ideas like distance, like midpoint, equation of a sphere, all of those ideas extend directly from our ideas in 2 dimensions. So distance, we use a distance formula. We just have one extra term under our square root. Our midpoint, we just have one extra component, one extra coordinate that we need to find the average of the coordinates to get our midpoint. Equation of a sphere, just like the equation of a circle, we just have one more term with a z in it. Our properties of 2-dimensional vectors extend to 3 dimensions. So those properties like equality, magnitude, the idea of a unit vector, all of those things extend. We just add another component: unit vector, addition, and scalar multiplication. So all the things we talked about yesterday in 2 dimensions, we can extend to 3 dimensions. And one important idea that we didn't talk about yesterday is that vectors are parallel if we have, for vector u and vector v, one is a scalar multiple of the other. So if vectors are scalar multiples of each other, then that tells us that they're parallel. In 3 dimensions are standard unit vectors. We just add one additional standard unit vector, and we have to add one component to each of our vectors. I hat is the vector 1, 0, 0. J hat is the vector 0, 1, 0. And k hat is the vector 0, 0, 1. All right. Whoops. All right. So let's look. I just want to go through one example of working with vectors in 3 dimensions because everything's really the same. We're just adding a component. So there's really not any new information. So let's say we have a cable and it's stretched between 2 points in space. So I don't know, one's at the top of a tower and one is anchored to the ground, for example. And we give those points in space. We set up a coordinate system and we say, oh, the cable goes between the points 1, 3, 5 and 4, 7, 9. So we set up some kind of coordinate system. We set our origin somewhere, and one end of the cable is at 1, 3, 5, and the other end of the cable is at 4, 7, 9. And we know that the tension in the cable is 50 pounds. So you set up your cable and maybe you put a little spring scale in between the two parts of the cable, and when you stretch it, the scale says 50 pounds. So we know that the tension in the cable is 50 pounds. We want to represent the force in the cable as a vector. So what would we do? It's going to have something to do with the magnitude.
Find a standard.
Combine them in component form. Right?
So we want to write.
Standard when it's at 0, 0, right?
We want to write the component. It has something to do with component form. How are we going to get a vector in the direction of the cable? Right? Isn't the cable goes between those points, so I can represent the vector from one point to the other point. I can come up with a vector from one point to the other point. So the vector between the points is, and someone already said it, what's going to be the vector between those points? 3, 4, 4. 4 minus 1, 7 minus 3, 9 minus 5. And we're saying, when we do the vector this way, we're saying that's the terminal point. We could do it the other direction. It would still be okay. All right, so there's a vector between the points. What's our problem with this vector? It's not a unit vector. We need a unit vector.
The cable is straight. It has a tension.
We need a unit vector in that direction because the magnitude of this vector is the distance between those 2 points. We don't care how far apart they are. We just want our vector to point in that direction. So our unit vector. Our unit vector is the square root of, or 1 over the square root of 9 plus 16 plus 16 times 3, 4, 4. So that's 1 over the square root of 41, 3, 4, 4. There's our unit vector in the direction that's pointing in the same direction as the cable. And we want to represent the force as a vector in that direction with magnitude 50. So the force in the cable as a vector, we could write as (50 over the square root of 41 times 344).
Is there a difficult symbol for unit vector?
No. Usually we just write U, just a U. but that's not, it's not, U is not always a unit vector.
But couldn't you just use like E sub U or something else, like a subscript, so you keep them all together?
You could, but there's not a standard notation for it. Yeah. Other than I hat, J hat, K hat. Those are standard unit vectors. Yeah.
If we have a number like with a square root or something, it's not pretty, should we always leave it outside? It's just
It doesn't matter.
Okay.
Yeah. If you had multiple cables attached at various points on the ground to this point, you could do the same thing with all of those various cables and then find the resultant force that's exerted on the top of the tower or whatever. If the resultant force wasn't zero, though, then the tower would be moving somehow. Right? Well, I guess it's the tip of the tower would have to be exerting the same force back in order not to move. So the tip of the tower would have to be strong enough not to bend. All right, questions? Yes.
So, find the force, you just multiply the tension by the unit.
Yes. Yeah. Because the tension is the magnitude of the force, and we wanted to know the direction also. If you would have set it up with this as the terminal point, this would have just been a negative. It just points in the other direction. And then it's just a question of whether you want the force that the top of the tower is exerting on the cable, or the force that the cable is exerting on the top of the tower.
So would you just say the net, the overall force would be absolute value, so it's positive because you can just flip it over?
Yeah.
Don't you normally just positive is to have positive?
Well, it would depend on the setup.
On the question.
Right, on the question. This one, it just says find the force in the cable.
So either would be an acceptable.
Either would be an acceptable answer. All right. Are we good? Okay.